Good afternoon, everyone. Welcome to today's 12th physics class. Okay, so I am excited to dive into a crucial and fascinating topic in current electricity. That is cells in series and parallel, and Kirchhoff laws and Wheatstone bridge. Clear? Okay. So these concepts are the bedrock for analyzing any complex electric circuits. Okay. So our goal today is to not just understand these principles, but to be able to apply them to solve a real world circuit problems. Okay. Able to apply them to solve real world circuit problems. Okay. So before we start, I want to share a quick thought with you. Think about the invention of the light bulb. Already you know that name, Thomas Alva Edison. So Thomas Edison. Yeah. So it was not one single flash of genius. It was a journey of over 10,000 failed attempts. 10,000 failed attempts. Okay. So when a reporter asked him, how did feel to fail 10,000 times? How did feel to fail 10,000 times? Edison famously replied, I have not failed 10,000 times. I have successfully found 10,000 ways. That will not work. That will not work. Very brave statement. Yeah. Very confident statement. So I have not failed 10,000 times. I have successfully found 10,000 ways that will not work. That spirit of persistence and learning from every attempt is exactly what we need in physics. Circuit problems, especially those involving Kirchhoff laws, can seem intimidating, but every time you try a rule, set up a equation or make a mistake, you are not failing. You are just eliminating a way that does not lead to the answer. Okay. So let's tackle today's complex circuit with the same persistent investigative spirit. Now, let's quickly test our prior knowledge from previous classes with a 3-question quiz. I am going to share my screen now. Okay. So this is a 3 MCQ. According to Ohm's law, if voltage is 12 volt, resistance is 3 ohm, what is the current? Very, very easy one. Yeah. According to Ohm's law, if the voltage is 12 volt, okay, resistance 3 ohm, then what is the current? Anybody? If you know the answer, you can tell or you can message me via the chat box. Yes, option one. Okay, good. Ohm's law. Already you know that the famous and simple formula. Yeah. Anybody? APRJC, Nagarjuna Scholar, GJC. Yes. Anybody? Yes. Good. Response coming. Anybody? Any schools? Any students? Very, very simple one. Ohm's law. Please remember that Ohm's law. V, I, and R. Yeah. So the ohms are related the three important quantity V, I, and R. That formula. Yes. Okay, good. Option 1. Okay, we can select and let me check the answer. Okay. So 12 volt, 3 ohm, 4 ampere. A means ampere. Okay, good. Okay, next. Two resistors, R1, 4 ohm, R2, 6 ohm, are connected in series. What is the equivalent resistance? Already you know that formula for the resistors in series and parallel connection. Yeah. Resistors in series. So you have two resistance value. One is R1 4 ohm and another one is R2 is 6 ohm. What is the equivalent resistance? Anybody? What is the equivalent resistance of the resistor in series connection? Good. Option 1, 1, 1. 1 means 2.4 ohm. Yes, correct. Okay. What is the equivalent resistance in series connection? Anybody? Any schools? Just remember your previous class topic, that is resistors. Today we are going to discuss about the cells. So cells in series, cells in parallel. Okay. Anybody? Okay, 2.4 ohm. Okay, let me check. Okay, later. Okay, right. And the final one, what is the equivalent resistance of the 8 ohm resistor connected in parallel? So previous question belongs to the series connection. This question belongs to the parallel connection. Here, what is the equivalent resistance of two 8 ohm resistors? So you have to know the equivalent resistance of the resistor parallel connection. What is the equation and what is the formula? Option B, 0.25 ohm. Okay. Okay. Anybody? Okay. One, one, two. Which one is correct? Okay. We can select 0.25 ohm. Let me check. Okay. Right. So, one. Okay. Okay. Right. Option in for the previous question, someone told 10 ohms. Oh, okay. All right. Okay. Let me check. Okay. Right. We score. According to the Ohm's law, if the voltage is 12 volt and the resistance 3 ohm current, so V is equal to IR. Yeah, V 12 volt, I we have to find that, and resistance 3. So 4 into 3 12. Okay, very good. So 4 ampere is the correct answer. Very good. Good. So V is equal to IR. Okay, right. Next question. Two resistor in connected series, then equivalent resistance formula, just you have to add the individual resistance. Yeah, someone told 10 ohm, which is the correct answer. Yes, but many of the students click the option 1. That's why I am putting option 1 here. Okay, so equivalent resistance in series connection for the resistors, you have to add the individual resistors. So R1 plus R2. So 4 ohm plus 6 ohm, we will get the 10 ohm. So 2.4 ohm is wrong answer. Okay. Option B is the correct answer. Good. And this is the opposite to the previous one. Yes. Here you can see that equivalent resistance of the 8 ohm resistor connected in parallel. Equivalent resistance formula in parallel connection, we have to reciprocal of the resistors. Okay, we have to add the reciprocal of the individual resistor. For example, 1 by R. This is a equivalent. Okay. So there is a formula for this connection. 1 by R1 plus 1 by R2. Is it correct? Okay. So here 10 ohm resistor, here 4 ohm. Okay. First of all, you have to think, you have to careful in this case because 1 by R equivalent. Okay, sir, 1 by R equivalent. Okay, here 1 by 8 and here 1 by 8. Okay, sir. So we have to take the normal LCM. Okay, so we will get the 2 by 8. Yes, 2 by 8. So cancel 1 by 4. Is it correct? 1 by 4. Then answer 0.25 is correct. No, we have to take the reciprocal because here we have a 1 by R equivalent. But the value of the equivalent resistance, we have to take the reciprocal. So 1 by 4 reciprocal of the 1 by 4, 4. That's why answer is 4. Clear? Clear? Okay, good. So these are the very important and very basic questions, which is very useful for you to remember previous classes. Okay. Okay. Let's quickly summarize the core concepts we will do using today. Okay. Right. Good participation, students. Very good. First of all, cells in series. So cell, another known name is battery. Yeah, because several cells can be connected to form a battery. Okay. So for example, this is a circuit symbol for cell. It has a EMF. So this is a EMF. Epsilon means EMF. This is a cell. So we connect this is a positive terminal. This is a negative terminal. Okay. So we connect the positive terminal of the one cell to the, here you can say positive terminal of the one cell to the negative cell of the another cell. Like that. This is a series connection. This is a series connection. So it has a EMF. It has a EMF. The EMF and the internal resistance, because every cell, every battery has internal resistance. Yeah, small r. We can write small r. Value may be varying according to that respective battery or cells. Okay. So it has a internal resistance, it has a EMF. Okay. Suppose cells are series, cells in series, EMF, equivalent EMF means total EMF. We have to add the individual EMF like that. Okay. Equivalent EMF means we have to add the individual EMF. For example, this is 1, this is 1, this is 1 volt, 1 volt. Then E equivalent 3 volt. Very easy. Yes, correct. Then next one, equivalent resistance. Equivalent resistance means same as well as EMF. So we have to add the individual internal resistance of the each cell, because this cell has a internal resistance R1. Okay, this cell has a internal resistance R2. This cell has a internal resistance R3, which means they are different to each other. Okay, R1 is different to R2, different to R3. Okay, right. So this is used when we need a higher voltage, like a flashlight. Okay, cells in series used when we need a higher voltage, because voltage sum of, if you add the 4 cell or 5th cell or 6th cell, voltage increases. So we will get the higher voltage, like in a flashlight. These are for cells in series. Now, cells in parallel. Now, cells in parallel. Already you know that this is a circuit symbol for cell. This is a positive connection. This is a positive negative terminal. That longer line denotes a positive terminal, and the smaller terminal means negative terminal. Okay, right? Okay. So here, all the positive terminals are connected together like that. All the positive terminals are connected together, and all the negative terminals are connected together like that. So this is a connection, parallel connection. Okay, clear? So in parallel connection, all the positive terminals of the cells are connected to one point. For example, here, or for example, here. Okay, like that. Okay, and then all the negative terminals are connected together to a single point. That is one point. Clear? Right. So already you know that each cell has a EMF like that. E1, E2, E3, and internal resistance R1, R2, R3, like that. Yeah. So here EMF remains same. Equivalent EMF means individual EMF, not a sum of. So EMF remains same. Equivalent EMF, which is equal to individual EMF. So here 3 volt, 3 volt, 3 volt, and equivalent only 3 volt. Clear? Equivalent EMF only 3 volt. And for the case of internal resistance, so we have a formula already. We know that resistance in parallel connection. So this is a parallel connection. Already I told the formula, that is 1 by R1, 1 by R2, 1 by R3. Clear? For example, this cell has a internal resistance 1. This cell has a internal resistance 1.5. This cell has a internal resistance 1.6, for example. Okay. So we have to put like that 1.5, 1.6 like that, and we have to take the LCM, and we have to take the reciprocal. So this is all for internal resistance. Okay, R equivalent, R means internal resistance. Internal resistance means already I told you, each cell, every cell has a internal resistance. Every battery has a internal resistance. Okay, so this is cells in parallel. This is used for a longer battery life, or when we need a higher current. When we need a higher current, or when we need a longer battery life, we have to take the cells in parallel connection. Clear? Okay. Next one. Kirchhoff law. Next one. Kirchhoff laws or Kirchhoff rules. Okay. So in Kirchhoff law, we have a two formula. One is current law, or we can say that Kirchhoff current law. Okay, right. At any junction, the sum of the current entering must be equal to the sum of the current leaving. Currents leaving. This is a definition for Kirchhoff first rule, or Kirchhoff current rule, or Kirchhoff current law. Okay. So it is state that algebraic sum of the current at any junction of the circuit is 0, because sum of the current entering must equal to the sum of the current leaving. This is a direct consequence of conservation of charge. Direct consequence of conservation of charge. Clear? So for this question, we can imagine one circuit. For example, So this is a junction. Here one current comes, I1. Here one current goes away from the point. So we can take I4. This is I2. I2 coming towards the point, and I3 going away from that point. And okay, this is I4. This is I5. We can label it any number. Okay. So I1 coming, I2 coming, I3 going, I4 going, I5 going, right? So two current coming, three current going away from that point. So according to this Kirchhoff first rule or current rule, I1 sum of the current entering must be equal to the sum of the current. Okay. So sum of the current entering must be equal to the sum of the current leaving. So I3, I4, I5. So if we add up the, so I3 goes here, so minus I3. I4 goes here, minus I4. And I5 goes here, minus I5. So I1 plus I2 minus I3 minus I4 minus I5, which is gives a 0. So the algebraic sum of the all the current at the any junction of a circuit is 0. This is a current rule, current law. Clear? Okay. Then next one, voltage rule or second rule or loop rule. Okay. We can say any name for this rule. KVL, Kirchhoff voltage rule or voltage law. Second law, second rule, loop rule. Okay. Voltage law. Okay. Here, the algebraic sum of the changes in potential, voltage drop, and rises around any closed loop in a circuit must be 0. Okay. So, definition, the algebraic sum of the changes in potential. So, maybe voltage drop or rises around any closed loop, around any closed loop in a circuit must be 0. Must be 0. Underline that word or you can take the notes. Clear? So this is a voltage rule. Note it down. Algebraic sum of the changes in potential, voltage drops or rises around any closed loop in a circuit must be 0. Okay? Right. For example, we can draw one diagram related to this figure. For example, um, see, so this is one connection. So A, C, uh, this is battery. So EMF, and this is a connection B. Okay, here you can see that one resistance. So I1 current passing through that R1, I1. Here R3, here R2. So this is I3. We can say that I2. Okay, plus R2, so I3. And here I5, R5. Here R4, I4, like that. Okay, right. So A, B, C. There are I1, I2, I2, I3, I4, I5, and resistance R1, R2, R3, R4, R5. So in this case, according to the closed loop, ABCA, this is a closed loop. Yeah, ABCA, this is a closed loop. According to the Kirchhoff voltage rule, voltage law, that is I4 into R4. So I4, right? I4 into R4, because I into R voltage, and goes here and goes here like that. Okay. So I4 into R4 plus I5 into R5 minus, because we are going from this place and to and here current passing opposite to the our loop. Okay. So we have to put minus sign here. I2 R2. So which gives 0. This is the voltage rule. So I4 R4 plus I5 R5 minus I2 R2, because here minus means current passing from A to C, but we are going from here to here and here to here. So that's why current is opposite to the our measurement. So that's why I am putting minus sign again. This is a Kirchhoff voltage rule, voltage law. Okay. Then next topic, that is Wheatstone bridge. Wheatstone bridge. So this is a special circuit which is used to precisely measure an unknown resistance. Okay. So Wheatstone bridge is a special circuit used to precisely measure an unknown resistance. For example, okay. So this is a connection, and here one gallon meter or ammeter is there. Okay. Right. Here it has four resistance. One is we can label it P, Q, R, yes, like that. Okay. P, Q, R, yes, like that. And the current going like, and here, and here, and here, like that, in this direction. Current. So I1, I2, I4, I like that, because resistance has a different value. So it has a four resistance in a quadrilateral arrangement. The bridge is balanced when there is a no current. The bridge is balanced when there is a no current passing through this column-meter. So the current passing through the column-meter is 0, then we can say that the bridge is balanced. So the bridge is balanced when there is a no current flowing through the column-meter. So the column-meter connecting between the middle of the 2 points from the from these 2 points. Okay, right. So the balance condition, P by Q equal to R by S. P by Q equal to R by S. So we can give any value, 4 ohm, 5 ohm, 6 ohm, for example, you can say that. So P by Q, which gives some value, 4 by 5, which gives some value. And R by S, so for example, like that, or 8 by 4, like this, for example, okay. So P by Q is equal to R by S. This is a balance condition. Balance condition is the key here. Okay. All right. Now let's see this concept in action. I'm opening the FET simulation. Okay. Cells in series and a parallel connection concept. I will share the screen now. So this is a FET simulation. From this simulation, we can see that cells in series and parallel connection. For example, already I told you this is a cell or parallel. Okay, right. So the longer line means positive terminal. I can place like that. Okay, and I can take another one. We can take any number of cells, but here I will take the three cell. Okay, and I am connected like this. Okay, and then we can take the wire. And we have to connect the ammeter in series connection to find the current passing through these circuits. Then we can add the switch here. And we can add the one resistor here. Okay, right. Like that. Okay. So suppose if you switch on the circuits, like closing the switch, you can see that current value. Electrons are moving. Yeah. Now you can see that values. Clear? So each cell has a EMF 9 volt, 9 volt, 9 volt, and current 2.70 ampere. And here external resistance 10 ohm. This is a 10 ohm means external resistance. Clear? Okay, right. Now we can add the internal resistance. Now you have to look at the current value just to see that. Yes. So I am increasing internal resistance 2 ohm, 3 ohm. In that case, you can see that the values of current changing because already we know that relationship between the current and EMF and internal resistance. Okay. So I is equal to E total EMF. So here total EMF means 9 plus 9 plus 9. Yeah. By total resistance. So total resistance means internal resistance plus external resistance. So internal resistance means 5 plus 5 plus 5, 15, and then 15 plus 10. Clear? That's why the value of current changing. Okay. For example, in cells in series, current, total EMF. Total EMF means number of EMF. So you can place any numbers, 3 or 2 or like that. Here, total resistance. So total resistance means number of the cells, internal resistance plus external resistance. So N, 3, 3, 4, 4. Yeah, because each cell has an internal resistance. So NR plus R. Clear? Okay. So in this case, for example, 3 EMF. Each one 9 volt, 9 volt, 9 volt. 3 into 9 volt. Because number of cell 3 and EMF 9 by NR. 3 internal resistance. We can say that 1. Okay. We can take as a 1 or 2 like that. And external resistance 10. 27 by 13. because 3 into 1, 3, and by plus 10, 13. Clear? So 27 by 13 gives 2.07. 2.07. That's why, okay, done. So that's why I am here. You can see that. Oh, 1 second, no, sir. Correct? So you can see that 1, 1, 1. 3 internal resistance. So 3 into 1, 3 plus external resistance 10. So 9, 9, 9, 27. 27 by 13. We can get it 2.07. Yeah. So you can here you can see that 2.08. This is a cells in parallel. Sorry, cells in series. Okay. Right. Now we can move into the another case, that is cells in parallel. We have to add the same terminal to the 1 point. Yeah. Like that. And then we have to add the one resistor, external resistor here. So we have to add the switch and the ammeter. So right here you can see that values 999 internal resistance. Okay. In that case, you can see that potential, that is EM of 9 ohm, 9 volt. Here 9 volt. And here 9 volt. Yes. So that's why I'm saying EMF same in a parallel connection. So 9 ohm, 9 ohm. So we don't add the internal EMF. So EMF, total equivalent EMF, which is equivalent to single EMF 9 volt. Clear? Right. Okay. So we will move into the numerical problem. Problem number 1. Cells in series question. 3 cells. 3 cells of 2 volt, 2 volt, 2 volt connected in series, having internal resistance 0.5 ohm. This is the internal resistance connected to the external resistance. Connected to external resistance 3 ohm. Already I told you that is there is an external resistance 3 ohm resistor. We have to find the current I here. So okay. Already I told you in series connection equivalent means individual. So 2, 2, 2. So 2 plus 2 plus 2, 6 volt. Clear? And equivalent internal resistance. R equivalent means R1 plus R2 plus R3. So 0.5, 0.5, 0.5, which gives 1.5 ohm. And total resistance means internal resistance equivalent internal resistance plus external resistance. So 1.5 plus 3 ohm, which gives 4.5 ohm. This is the total resistance. Okay. So we have a total EMF, total resistance. Then formula for current, already I told you the formula for current, I is equal to total EMF by total resistance. Total EMF, we have a 6 volt, yeah, 6 volt by 4.5 ohm. So 6 by 4.5, which gives 1.33 ampere, which is the current value for this case, for this problem. Okay, all right. Next question, parallel question. Parallel question. 4 cells. Each have a EMF 1.5 volt. Internal resistance 0.3 ohm. Connected in parallel. Okay, 4 cells. Each has a internal EMF 1.5 ohm. Internal resistance 0.3 ohm. Okay, connected in parallel. Find the equivalent EMF and internal resistance of the combination. Okay, for this sum, equivalent 1.5 volt, because each cell has a 1.5. So equivalent EMF 1.5 volt. Already I told you 1.5 volt. And the equivalent internal resistance, R equivalent means 1 by R1, 1 by R2, 1 by R3, 1 by R4, because here 4 cells, right? So R equivalent means 0.3 ohm by 4. Clear? R equivalent. You have to take the reciprocal. Then you will get the 0.3 ohm by 4. So which gives 0.075 ohm. This is a value for R equivalent in this case. Clear? Okay. So now I will share the 5 MCQ screen. Okay. Once again, I will share the screen now. Yeah. Okay. So first one, when cells are connected in series, the total EMF is. When cells are connected in series, the total EMF same as one cell, sum of the individual EMF, product of EMF, average of EMF. Which one is correct? Which one is correct? Very good. B. Yes. Sum of the individual EMF. Yes. Good. Correct. Right. Then next one. When identical cells are connected in parallel, the equivalent EMF. So now cells are connected in parallel. Then E equivalent EMF, sum of the EMF, product of EMF, same as one cell, half of total EMF. Which one is correct? For the second question. Option B, option C. Which one is correct? Option B, 2, C, B. When identical cells are connected in parallel, the equivalent EMF. Already I told you the 9 ohm, 9 volt, 9 volt, 9 volt. And this in this that case. C. Okay, good. Yes, C is the correct answer. So the equivalent EMF, which is the same as one cell EMF. Okay. So option 3 is the correct answer. Very good. Clear. Good. And the next one. According to Kirchhoff current law at a junction, according to first rule, that is Kirchhoff current law, the sum of the voltage drop is 0. Sum of the entering and leaving currents equal. product of currents or current constant, power is conserved. Which one is correct? According to Kirchhoff current law. Yes, very good. Yes, yes. Option 2 is the correct answer. Yes, many responses. Option 2. Okay, good. Sum of the current entering and leaving must be equal. Yes, good, good, students. And the fourth one, in a balanced Wheatstone bridge, the current through the collimator is very important one and a very crucial one. Yes, very good. Yes, 3. Good. Yes, many students answering option 3 because very important. In the Wheatstone bridge, we can say that balanced means the current through the collimator is 0. Yes, good. 0. And the final one. The Wheatstone bridge is mainly used to for what purpose? Measure electric current, measure potential difference, measure unknown resistance, measure internal resistance of the cell. Which one is correct? The Wheatstone bridge, yes, APU or JG, you are telling correct answer. Yes, very good. Good. The Wheatstone bridge is mainly used to, which one is? Yes, good. Measure unknown resistance because we have here 4 resistance in the Wheatstone bridge P, Q, or S. Suppose if we know the other 3 resistance, for example P, Q, R, then we will measure the unknown resistance. That is a 4th resistance. Yeah, that's why I am saying Wheatstone bridge is mainly used to measure unknown resistance in the class. Yeah. So let me check answer. When cells are connected in series, the total EMF, yes, sum of the individual E1, E2, E3 like that. And when identical cells are connected in parallel, the equivalent EMF same as one cell. Yeah, E equivalent equal to EMF of the each cell. That is one cell. Okay, so same as one cell. Very good. And the third one, according to Kirchhoff current law, the junction, the sum of the entering and leaving currents equal. Good. And the fourth one, in a balanced Wheatstone bridge, the current through the galvanometer is 0. Good. And the final one, the Wheatstone bridge is mainly used to measure unknown resistance. Clear? Good. So now is your turn to ask any questions, any doubts? Any doubt? Any volunteer to explain why we use the parallel combination of cells if the EMF does not change? Or you can say that any Kirchhoff rule, first rule or second rule. Any students? And what is condition? What is the bridge condition in the Wheatstone bridge? Anybody? P by Q is equal to R by S. Yes. Very good. Okay. Right. So we learned that cells in series increases voltage while cells in parallel increases current capacity. And Kirchhoff current law and voltage law, which is essential for solving any complex circuit. Okay. Because consideration of charge, consideration of energy, okay. And in the case of Wheatstone bridge, the balance condition P by Q is equal to R by S, and it is practical use in precisely measuring the unknown resistance. Right. Okay. Now is the time to take down the homework. I will share the screen. So this is a homework. Take down. Please write it down. First sum. A battery of 4 cells in series, each with an EMF, electromotive force, so 1.5 volt, internal resistance 0.2 ohm, is connected to the parallel combination of 6 ohm and 3 ohm resistor. Calculate the total current and the terminal voltage of the battery. So terminal voltage means nothing but normal voltage between the terminal, positive and negative terminal. Yeah. So that's why it is known as the terminal voltage of the battery or terminal voltage of the cell. Because here terminal voltage of the battery means battery is nothing but several cells are connected to form a battery. So in battery, it has a 3 cells, 4 cell according to the requirement. Okay. Right. And the second one, write a brief paragraph about 100 words explaining one real world application of Wheatstone bridge in strain gauges, thermistors, or light dependent resistors, and describe how the principle of balance is used in that application. Very important one. Okay, you can search in the internet about this question. You will get the more and more important details. So that is a practical purpose. Just to know that P by Q is equal to R by S, okay, but it is not enough. Okay, you have to think beyond the textbook. So that's why I am giving that question. Okay, any doubts? Okay, thank you, students. Thank you, teachers. Thank you, Vidyashakti. Jai Bharat, Jai Hind.